Well, thank you everyone for coming today. Our seminar is titled Deterministic Annealing for Clustering, Compression, Classification, Regression, and Speech Recognition. And our speaker is Professor Kenneth from the Electrical and Computer Engineering, University of California, Santa Barbara. Professor Rose received his PhD in electrical engineering from Caltech in 1991, and his interests are in information theory, source and channel coding, speech in general, pattern recognition, and many other things as well. And notably, in 1990, he received the William R. Bennett Prize for the best paper in the IEEE, from the IEEE Communication Society for the best paper in the transaction. So, thank you, Professor Rose, for speaking to us today. And I would like to tell you that he has a very tight schedule. He has to leave here at 5:30 exactly, so I don't know whether to tell you to save your questions for the end or to ask them during the middle. But in any event, if you're going to ask them, please keep them to the point, because we want to make sure that he doesn't spend another night here. So, thank you.
I suggest if you have hard questions, save them to the end, and then I'll just run away. Okay. I suppose after looking at this title, some of you wonder if deterministic annealing could also do the dishes and do the laundry, and the answer is probably yes. Okay, I have to acknowledge there's a whole bunch of people who were involved in various parts of this work, that it covers several years of research. And there are Jeffrey Fox, Liang Gu, Eitan Gurwitz, Cecile Hui, David Miller, Jayant Nayak, and Ajit Rao. Much of the early material I'm covering this talk can be found also in this paper in the proceedings of the IEEE in November '98, but that paper does not cover the speech recognition material. Okay, the organization of the talk. The first part, we'll talk about clustering, data space partitioning. More generally, there are a whole class of problems that have to do with data or space partitioning, and one special problem is clustering, which is the easiest to get intuition for, and that is why we're going to look at the method deterministic annealing, mainly within the context of clustering. After which, in part two, we'll see how we extend this to address problems of supervised learning. That will include classification, regression, estimation, prediction, and part three will talk more specifically about speech recognition. Okay, so here we go. I would like to convey to you that we're talking about a fundamental basic problem on which we can construct solutions to a lot of different fairly important problems. And the basic thing we're looking at is the design of signal processing systems for signals of unknown or somewhat known statistics. And the problems that we're looking at are clustering, in particular application in compression and in data analysis, pattern classification, of interest here, speech recognition, all sorts of graph theoretic problems that I will not cover at all, and functional regression, prediction, interpolation, estimation. All of these are going to involve, in one way or another, the problem of partitioning the space or the data in some optimal way. Here's the example of clustering. We have a bunch of data set that we want to get some statistical handle on, so we're looking for a structure, so we look for an optimal way to partition it. So that's the problem of clustering. It's called unsupervised learning. Similarly, classification is the problem when we have a data set, but it also has labels, and what we're trying to design is a machine or a partition that will help us separate samples that come from the different classes when we don't have access to the labels. So this is supervised learning because we assume that some supervisor or teacher took the trouble of labeling this training set for us. If you look at the solution to the classifier problem or the classifier design problem, The optimal solution is the Bayesian classifier that computes the posterior probabilities of each class given the observation and chooses the most probable one. That's a well-known result. If we look at a problem of functional regression, we're trying to find a function g of x that would give us the best estimate we can of y. So we have x and y that are correlated vectors. And typically you would minimize the mean squared regression error. That's there. And the solution, the optimal solution, is of course the optimal estimator, which is the conditional mean. In the case of clustering, we have these samples and we try to assign them to clusters or to code vectors, and we minimize the clustering cost that I didn't take the bother to write here, and an example is vector quantization in compression. So what we have is the theoretical solution that we saw. The optimal solution requires knowledge of the statistics or the probabilistic framework or the probability distribution of everything. But that's not usually available. So what we have to do in practice is to design algorithms based on a training set of data that gives us some idea of the statistics. One could go the route of just take the entire training data set and try to estimate what are the probabilities and then use the previous solution. But in most cases, more efficient solution is to just extract from the training set whatever is relevant to our solution for our problem. Because you need less training data than if you needed to actually estimate well the statistics. Okay, a parametric design, we'll be restricting everything we say today to parametric approaches, is we choose a structure or a parametric form for the system, and then we adjust the parameters so as to optimize the performance on a training set. There's always the big question of what happens outside the training set, and we may touch on it occasionally, but not really seriously during this talk. So if we return to our classifier design, the optimal solution was compute the posterior probabilities and choose the most probable class. This is going to be replaced by a parametric form, where for each one of the classes we now have a discriminant function, and we just choose the maximum. And this function depends on a set of parameters lambda, and when we design, our objective is to find the best choice for these parameters so that we'll make as few errors as possible. Similarly, in regression, that was the optimal solution, the conditional mean. We'll replace it with some parametric function that we have to find the best parameters for. Okay, now let's focus on the problem of clustering, and I chose it because it's the simplest of all problems and it's the easiest to convey the basic ideas of the method. So the problem of clustering in vague terms is we have, let's say, a training set, and we want to partition it in some optimal way into subsets that are as homogeneous as possible. Of course, to make this precise, we have to define a cost function, and the cost function of the type we'll be dealing with will be an additive one, and here in this case we call the distortion. This is terminology that is taken from the compression literature. The distortion is you sum over the clusters, J, you sum over the points in each cluster, and the contribution that each point contributes to the distortion when it's associated with this cluster. So that's the total cost function for a clustering solution. Standard methods. This particular thing has been developed in different fields by different people. I would say at least somewhat independently, and it has different names in different areas. And every few years we discover that somebody even discovered it earlier, somebody else. So standard approaches in the compression literature, you'll see the generalized Lloyd algorithm, which was an algorithm for designing originally scalar quantized or extended to vectors. K-means in the pattern recognition literature, you may have run into ISO data and other names too. What is the basic idea? The basic idea is pretty simple. We break are designed into iterations that consider two subsets of the parameters we're dealing with. The first step, you say we're given a code book, y, and now we assign each training vector x to the nearest code vector. And that's the partition design. Nearest here is in quotes because nearest in the sense of our distortion measure that we define. It's important to this problem. So we design the partition given the code book. The next step is say let's fix the partition we have and design the code book for this partition, which means finds the best possible code vector for each subset. Obviously, since each time we're doing the best possible choice, we're finding the best possible choice, fixing the other half of the parameters, we keep decreasing the distortion. So this thing decreases and decreases the distortion until it stops, and that's where we found a solution. Now, the difficulty with this is at the same time is that there is no guarantee that this solution is the global solution. It's maybe just a local minimum where these two steps, we reach a solution based on those two steps. You're not going to change. Given this code book, this is the best partition, this is the best code book, but there may be something much better with a totally different partition and a totally different code book that is out there. So this is the motivation for the deterministic annealing or DA approach. The first take on it is we say, let's just temporarily randomize the partition. Temporarily means for the purpose of the design. We are not going to, in the end, be using some kind of random clustering solution, but just for the purpose of the design. So a training vector x is assigned to code vector y with probability p of y given x, where of course these are normalized to 1. So instead of assigning, so in fact the usual case is the special case where the probabilities are either 1 or 0, but we want to look at it in general. So what we mean is, here is your standard technique. You take a sample point and you assign it to the nearest code vector. What we do now is this. We assign it to everybody in the code book, but with different probabilities. Now, we define just a formal structure of probabilities. Now, we want to find what is the probability distribution that we should use. So what we look at is the now expected distortion. Since now points are assigned in probability, we have an expected distortion, which is simply written there, that involves the assignment probabilities. We're assuming here, just for completeness, we have P of x, but in the case of a training set, it will be just 1 over the length of the training set. So we want to minimize the expected distortion over the code book y and the random partition p of y given x. Now, we need something. If we were just to stop there, the optimal partition would be still a hard partition because it's always advantageous to assign a point completely to the nearest code vector. It gives us less distortion than to spread it also over distant ones. So what we want to do is minimize this expected distortion subject to a constraint that tells us how much randomness we impose on the solution. And this is measured by the Shannon entropy, which is written down there. One could use the joint entropy. I'm using the conditional entropy since the h of x is a constant. It just depends on the training set and not on our solution. So this measures our randomness, and given, let's say, we impose a particular level of randomness, we have a solution that is normally random. So what the problem that we're having is minimize d subject to h equals some value, h naught. Of course, we can write it as a Lagrangian, minimize f, which is d minus th, over the random partition and the code book. T is a Lagrange multiplier, and the funny choice of notation will become obvious now. There is a very strong analogy to statistical physics in the way we're doing things. If you look at this equation, f equals d minus th, even in a superficial level, you may recognize a sort of cornerstone equation in statistical mechanics, thermodynamics, which is the Helmholtz free energy, where if you assume that d is the energy, t is the temperature, and h is the entropy, then F is the free energy. If we minimize F at a given temperature, we're just finding the isothermal equilibrium of the statistical mechanics system. And if we look at what happens to this at very high T, very high temperature, you look at this Lagrangian, you see that you're effectively just maximizing the entropy. That's the minimum of F. When you lower T, when you approach zero, we're just minimizing the distortion, which is what we plan to do. So you already can see why we're looking at annealing, which says let's start at very high temperature and gradually lower the temperature. At the limit of T goes to zero, we'll be actually minimizing what we wanted to minimize. And there are lots of advantages that come out from the physics analogy, which is everybody knows that annealing is a way of trying to avoid bad local minima, which is what we're trying to do here. If you look at the optimal distribution when you you minimize the free energy with respect to the assignment probabilities, you find that it's a gift distribution. That's written there. I don't know if this is very easy to see from the back. But the properties of it are very promising, because you see, we give higher probability of assignment to a nearer code vector than to a more distant one. And you can see that when the temperature is very high, you get a uniform assignment. When the temperature is very low, you get a hard assignment with probability 1 to the nearest code vector and 0 to all the others. And everything in between is in the middle. We also want to minimize with respect to the codebook. And if we just take the derivative and set to 0, we get this equation. But to get more intuition, let's look at the squared error special case for the distortion, in which case you see that the code vector yj is simply the centroid of the posterior distribution given the cluster, p of x given yj. So this is just a generalization of your old centroid rule that you have in regular clustering. It's just a random generalization. So as the temperature goes to 0, you can see also that this approach becomes GLA, because temperature goes to 0, we just the assignment probabilities become nearest neighbor. We just assign each guy to the nearest code vector, and the centroid rules is the old centroid rule that you use in GLA. But you also get maybe the first glimpse of why it might work, because think of it, when you're at temperature 0, the classical case, every point in the data is only affecting the nearest code vector to it. So you see how easily the system falls into a local minimum that has nothing to do possibly with the global optimum. But what we do here, we start at very high temperature where each point equally affects everybody, and then we gradually localize the effect so as to, at the limit, actually minimize the distortion. So the algorithm, roughly speaking, is we start at some initial temperature. Of course, it's not necessarily infinite. We'll see later why it doesn't have to be very high. We minimize the free energy. We lower the temperature by multiplying, say, by alpha less than 1, some annealing schedule. We do that as long as we are greater than some final temperature, which will normally, in this kind of schedule, will not be 0. And then repeat that until we reach that final temperature, and then we can jump to 0 and do, in fact, GLA, but with a very special initialization. Just to remind everybody, randomness is only maintained during the intermediate stages of the design. It's not the purpose the way I presented here, even though there are possible applications where you might be interested in the intermediate solutions. For example, some clustering applications where you want to consider fuzzy associations. So that's another sub-area that I won't be touching on really. Another thing to remind everybody, this is not simulated annealing, at least not what is usually referred to as simulated annealing, because we are not rolling dice and going up and down on some energy surface. while making some incremental progress on the average. What we're doing here is we're working with expectations and deterministically minimizing them as we lower the temperature. So we're working with the free energy viewed as an expectation. Okay, now I think it's worth it at this point to take a step back and give you a little more of a physical analogy. Let's take a viewpoint that would be taken by regular statistical mechanics people. They would say, let's consider all possible hard clustering solutions and put a probability distribution over them. So each one of these solutions is a hard clustering, just a particular partition, hard partition of the training data and a particular code book. So I write P of Sy as the probability distribution over all possible hard solutions. And the principle that people would use in physics is to say two solutions that have the same distortion should have the same probability of being chosen or occurring in this stochastic system. So once you do that, you can very easily find that your distribution over all possible hard solutions is the Gibbs distribution that's written there. That's over all possible choices of partitions and codebooks. And this can be obtained by just using maximum entropy one way. So assume that you have an average distortion. You get a Gibbs distribution as the maximum entropy distribution over all solutions. Or alternatively, you can say the opposite, say let's fix the entropy and try to minimize the expected distortion. You just get the same thing. It's Lagrangian. We're just switching the Lagrange multiplier from one side to the other, and we typically use beta for one and t for the other. But otherwise, it's the same thing. Now, the problem is that we have a distribution over a huge combinatorial set of possible partitions, and that's not very convenient, so we would like to look at the marginal P over Y, the codebook. So we want to sum up over all possible partitions, which gives us that expression over there, and we want to find what that is. That is, sum out these S's. So how do we do that? Well, okay, there's a name from physics for this expression, which happens to be the partition function z of y. And here we use a trick that, unfortunately, repeatedly I've come across the fact that it's much more difficult to explain it than to understand it. So what you have to see here is that we have all possible combinations of partitions there. It's just, you can think of it as discrete variables that tells you, okay, they're 1 or 0 if point X in the training set should be assigned to cluster J, and so on. So you have a bunch of possible combinations, and we look at what you have at the exponent there is D is really a sum over on the training set of expression of D of X, Y, J there, if you remember. So we can write it as a product over X of e to the minus beta dx and the cluster chosen by that particular partition for that point. And you can see that this huge summation is equivalent to a product of sums. Well, that's the thing that is more difficult to explain, but you see that since we're covering all possible partitions, this is the same thing. This will be, if you just multiply out this product on the right hand, you see that you get all possible partitions and exactly the same thing. If you notice that, now we're ready to define the free energy as minus 1 over beta log of the partition function, not to be confused with the partition of z, as is done in physics. And this is really this expression, because this product becomes a summation, and we get this expression. And now we summed out all the partitions S, and we're only dealing with the code book. And remember, before I click, that P of y was really z of y over all y z of y. So I can write it as e to the minus beta f of y, a Gibbs distribution. Now our function at the exponent is the free energy, and the most probable code book is the one that minimizes the free energy. So this is just repeating the expression for the free energy, and remember at t equals 0 it becomes the same as the distortion. And everything else follows. If you now take the derivative with respect to y, you get the same result that I gave you before. It's just a different look at things and more in line with what is typical in statistical mechanics. Okay, now there are sort of interesting and exciting things that happened when we look more closely at this. We look at this and see what happens at high temperature. All the code vectors will coincide at a point which is the centroid of the entire data set, because remember, the assignment probabilities are uniform. So all the data points, the training data, equally impacts all the clusters. So their centroids of everybody is going to be the same point, centroid of the data set. So effectively, we only have one cluster. We have, if you want, lots of clusters, but they are identical. They are the same one. Now, as we lower T, the temperature, at some point, there will be a split. And this is a critical temperature. And it will split normally into two, sometimes into more, subgroups of code vectors. So we have a few more clusters, but not as many as we had code vectors that we thrown in. And this is a phase transition. The effective number of clusters grows in a sequence of phase transitions. So we get a gradual increase in the complexity of the solution. We can actually compute the critical temperature, and I'm not going to give you the details, but it is directly related to the largest eigenvalue of the covariance matrix corresponding to that cluster. So we know it for every phase transition as future clusters split. Whenever there is a direction along which the variance is greater than something related to the temperature, that's the time to split. Okay, so the temperature relates to the variance of the cluster. So we know how to compute those phase transitions. Here is an illustration of the situation. So you have an example here of 1, 2, 3, 4, 5, 6 Gaussians. That's a mixture with centers marked by X. And here is a very high temperature solution. You see, you have one code vector at the centroid of the entire data. We start lowering the temperature, and then we have it split into two. We lower it further. We have 3, and here I used, just to remind everybody that these are not hard associations. Every point in the training data is associated with probabilities with the different clusters. So these are lines of probability third. That's why they meet at a point here. Okay, so you see how you have those fuzzy clusters. We go further. We have 4, 5, 6. That's the way the procedure evolves. In this case, you find what is very likely the optimal solution. Another example that I took from another place, just to show you, you can work also, even though we won't have time to cover this, you can work with clusters of different populations, different masses. So this is a more difficult problem, and this is a comparison we had in one of the papers, where you can run GLA 25 times, and the best solution is this one that is suboptimal, obviously, because it's cutting through a real cluster of high mass and missing out on 2 clusters up there. And this is the result of deterministic annealing in a single run. That's just an example, but this involves also having mass variables that I didn't really cover. That gives us also the direct relation to rate distortion theory. Okay, so now is the time to see the next big step, and that was, we wanted to also handle problems of supervised learning, where you have those, for example, classification with labels and so on, where the partition doesn't come out directly from your distortion measure, as it does in clustering, vector quantization. So the idea is we need to impose a structure on the partition now. You can't allow any partition, you need to impose a structure, because you don't want just to circle out all the points with label blue and circle out all points with label green and say this is my partition. That's too easy. So the solution that we propose is applicable to the design of very different systems. For example, multi-layer perceptrons, radial basis functions, mixtures of experts, vectors, quantizers. This is of interest when you do want to impose a structure on them as well, tree-structured or multi-stage. Decision trees, hidden Markov models, and of course, well, this is a sales pitch, lots of applications. Okay, how do we state the problem? we say we have a training set, and we have a parametric family of structured partition function. Now we have a bunch of parameters that define the partition. So S sub omega, where omega is a set of parameters that determine the partition. And we perform the optimization, minimize over omega and lambda. So we have parameters for the partition and parameters for the models we may use at each cell of the partition. That's lambda j. So this is pretty general because it covers problems of regression, classification, etc. So the particular case of classifier design is just this. We have a training set of points and labels, and we want to minimize the parameter set omega over the parameter set omega, the misclassification error. And piecewise regression, similar thing. You want to partition the space and put a local model in each place, and so as to minimize the regression error. Structurally constrained VQ is a kind of amusing result that we could go back now to VQ and show that actually now you can impose structures on it and solve problems that for in some applications you may want to impose a structure because you want to limit the complexity of the solution. A vector quantizer may have too many vectors in the codebook, so you want to reduce the complexity, you impose a structure. Okay, what we do is we put the partition in a canonical form, which means it's a maximizing a discriminant form. That is, we define some discriminant function for every cell of the partition, and maximizing it will give you the answer, the assignment of a point to a cell in the partition. It is easy to convince yourself that any partition in the world can be put in this way, possibly with a complicated set of discriminants. So this is the canonical way. So the partition function S of x is just the argmax of the discriminant function. So that's what determines the partition. Now, this looks silly, but what we're saying is let's write it in a way as if we have some function, some binary function that determines the partition, and we write a cost function whose maximum is obviously the exact partition rule that we had before. Okay? The idea is that we want to have a functional that we maximize. And that allows us to replace it now with a random variant, where instead of 0-1 decisions, we now have probabilities. So we still say we maximize this functional to obtain a randomized version of the structure and position that's going to impose completely when these probabilities are going to become 1 or 0. Maximizing this thing is going to, at the limit, give us exactly the partition. So again, we have the same old story. If we were to just maximize it as it was, we would get a hard partition, but we have to impose a level of randomness, and we get a constraint on the entropy. And again, surprise, surprise, we get the Gibbs distribution as the way we would implement our random partition. There's something funny that happened there. Should have been gamma, I guess. Okay. So we have this partition, randomized partition, which is really proportional to e to the gamma, the discriminant. And as gamma goes to infinity, region with highest score is chosen with probability 1, and that's the structure. The structure is imposed. For finite gamma, we randomly choose a region we imagine that we randomly choose a region. Of course, we're going to do expectations eventually. Okay, now we shouldn't forget that the whole point was still this was just to impose the structure, but we still have to deal with the thing we wanted to minimize in the first place. So now we plug the whole thing into, we have this distortion, could be the regression distortion, for example, that we want to minimize. Okay, we just produce a form for the random distributions that imposes the structure for us. Again, we want to minimize this subject to the entropy of the partition. And all we need to do is use the pj given I of the form that we have obtained from our way of implementing the structure. So you optimize this. Maybe I have it on the next slide. So we have this Lagrangian again, d minus th. We minimize it with respect to the parameters and gamma. And that's it. And that imposes the structure that we wanted on the solution. Some tested application, this just gives a summary of things we've done. Structurally constrained clustering, tree-structured VQ, multi-stage VQ, classifier design with all these guys, multi-layer perceptron, radial basis functions, learning vector quantizers, piecewise regression, classification in regression trees, or the competing method, mixture of expert regression, hierarchical mixture of experts, normalized radial basis functions. All these things have been done in different papers. And now we're ready to jump into the HMMs. Okay, this is probably going to lose on everybody here. This is a nice thing that my ex-student Ajit prepared to show people who don't know that much about speech recognition how we think of speech. This is in the case of a discrete HMM. Obviously not necessary here. And of course this is also useful model HMMs. I think I can skip that too. Oh, we got lots of fancy stuff still going on. Okay, but it all boils down again to our canonical form of classification. We just have a bunch of discriminants, and we're going to choose the maximum. The discriminants now depend on H. Unfortunately, here stands for HMM, not for the entropy. So a particular model, and we're going to choose the class for which a model produced the highest discriminant. The usual thing to do is looking at the likelihood. And we look in all the models. Again, this was tailored for people who don't know that much about HMMs. So you look at a trellis, and each pass corresponds to a sequence of states, and you want to find the most likely one. And so the class discriminant for a particular HMM will be the likelihood of the most likely path. So we have competition between paths, and the winner is the HMM that contains the most likely path. Difficulty is this. We have, the problem. Before the difficulty, we have the training set labeled. We want to design these J models to minimize the number of misclassified observations. Why is it difficult? Because it's a piecewise constant function in terms of the parameters. If I infinitesimally change any one of the parameters, I'm not going to switch any one of the training data from one class to the other, and therefore we get gradient zero everywhere, almost. So that's what makes life tough with this problem. And many people decided to use maximum likelihood for that reason. It's based on the assumption that the HMM is a correct model to begin with, because we built all the probabilistic expression on that. And we design each one of the model separately based on the training data that correspond to that label. And there are lots of nice things, like a bound-well tree estimation that makes life a little simpler than it would have been. And there's the problem that it's suboptimal. Suboptimal for a few reasons. One of them being that it's not the right criterion, not exactly the right criterion. Secondly, it assumes that you have enough data in the training set. Even if it were the right criterion, it wouldn't be so great if you didn't have enough data, and so on. So the alternative is, of course, to just directly optimize the right thing, the thing that we intended to do, And that's called usually discriminative training. And what it involves, first of all, that has to be taken into account is you have to handle everybody at the same time. Because now we're working at trying to separate things. We're no longer trying to model each one separately. So we have to take into account to jointly design all of these guys. There are descent methods for direct optimization. One particularly, the closest, in fact, to what we're going to propose is the generalized probabilistic descent, which says, okay, let's take this piecewise constant function and smoothen it. We just get it smoother, and then we can use gradients. That's the idea. What's missing is, still the problem is, as you may have seen, there are still lots of not so good optima out there. So you smoothed it, you still, depending on where you start, you're going to fall probably in a nearby minimum. You may be lucky or unlucky, that depends on the distributions of good minimum. DA approach, now this is the usual mantra. Temporarily allow random classification. Okay, so let's see what we mean. The standard H&M classification, you get an observation, you find the score of all paths in principle, and you choose the path with the highest score. Probability of error is fraction of times you'll be choosing the wrong HMM. In DA, you take the observation, find the score of all paths in principle. Of course, you're not going to enumerate all of them, and assign probabilities to choosing each one of them. I'm going to choose each one with different probability. And probability of error is the probability of choosing a path that is not the correct HMM. I hope the distinction is clear between the two things. So the regular rule is somebody is going to win. The randomized rule is everybody is going to win, but with different probabilities. Okay, so we get back there. So we choose a random path. Now I'm not going to go through it again, so you can imagine that you're not going to be extremely surprised that it's going to be a Gibbs distribution over all possibilities. Okay, that is proportional to E to the gamma, the likelihood of the path. Now here is a plug-in slide that I put in, especially for people who are knowledgeable about speech recognition, because that's where the confusion usually arises. When we say P of S given Y, we do not mean the posterior probability born out of the HMM of that the path, the sequence of states S produced the observation Y. We don't mean, we ignore completely for now that the structure of each hidden Markov model corresponds to probabilities. What we mean is the probability that the classifier will choose that set of states. So I make this point because notation is almost is the same, so people get confused. We mean this is the randomized classifier decision, not what the model is producing. Okay, so now a probability of error is just this expression. You can see that this is just based on the probability of choosing the particular path. So already it's a nicer, smoother function, by the way. And now the entropy of the classifier decision is as expected. And our good old free energy, which is the probability of error, the expected probability of error minus T times H. And you optimize it or minimize over the parameters of the hidden Markov models. And this was supposed to be gamma. Let's get another version of this funny thing. And the algorithm start at some initial temperature, minimize free energy to equilibrium, lower the temperature until you reach some final temperature, and then there is a quenching step where you go to zero, because we're not really going with this schedule all the way to zero. So you're going to stop somewhere, and that's the question?
Yeah, you're computing the entropy of the paths for the H term. Can that actually be done by dynamic programming? On the previous slide.
Yeah, but anyways, the actual update equations just are born out of derivation based on this. You're not actually computing this entropy. It's just, it's part of the f, and then we find derivative, and you get some update equations that are simpler. You don't need to do that. Okay. It turns out, again, I won't give you the details, that there is an equivalent low complexity forward-backward algorithm. That was a concern when we started coming up with this, because if we had to actually enumerate all the paths, that would be really of no interest to anybody. But you can do a forward-backward algorithm to do the DA version. And again, the usual reminder, the randomness that we have here disappears at the limit of zero temperature, and then your hidden Markov model may be random, but your decision is not random. Okay, some experiments that are taken out from our papers, and they're usually pretty naive, especially talking to this kind of a group. I have to warn everybody. As you may have guessed, we're not really from this area. We just jumped in with our tool here. So we use all sorts of little pet problems and databases that we could get our hands on just to show the possibilities. First, we've done an experiment on synthetic data sets, which means we just generated some data from hidden Markov models and wanted to see if we can get a better handle on it than the standard approaches. And that also allowed us to easily generate lots of data, because if you have synthetic, you can just generate as much as you want. And so these are the parameters of the experiment, and these are the test set results. So the red is maximum likelihood. This is, I guess, probability of error. Maximum likelihood is red. This is supposed to be GPD. At some point we called it GD, generalized probabilistic descent, is the second guy. This kind of green is DA. And then yellow is Bayes. Since we generate this synthetic database, we can actually calculate the Bayes. And as you can see, DA is doing a pretty decent job of minimizing classification error. And in fact, nobody is screaming yet. We do the impossible. We actually beat Bayes in this set. And this is to show you that even 10,000 test sets may be too short. It's just a fluke. We just beat it by chance. For this test set, we managed to get a little lower result. We're not really beating Bayes classifier. It's not a revolution in the field of pattern recognition. Okay, and then we did some speech recognition results, again, pretty naive. We took the E set, which is known for it being difficult because there are lots of similarity, B, C, D, E, etc. Front end, I'm not going to talk about it. Okay, and all this is discrete HMM design, by the way. I should have said that. Okay, that's what we used, and these are this is the speech data. We compared maximum likelihood and DA. This is, we had it in different sort of environments. So we did it with clean car noise and white noise. And this is, I believe, the training set results. And you see pretty big improvements. Performance on the test set, okay. We did an experiment for test set results. And as you can see now, the improvements are not as dramatic, but they're still there. You can see also in our experiments that for car noise, for example, the GPD did worse than maximum likelihood. That happened occasionally in our experiments. We did some continuous H&M work. The first one was extremely small, two-stage model, but you already see that in the training set we get amazingly big improvement, but in the test set it's still pretty respectable. Unfortunately here we have two reds, but the good one is DA, in case anybody wondered. We also increased to 6 states, which was an overkill for the problem. As you can see, we're even getting the training error lower, but there's still some improvement in the test performance, so it's not really. Okay, and here this, I don't know if this is visible. I'm afraid maybe not. These are much later results that we've got recently with tied mixture hidden Markov models, where we optimize the codebook of Gaussians and the mixing coefficients and so on. And on this one you can see maximum likelihood, training test, and then GPD, and then DA. And the other one was just to show how insensitive to initialization we all are. This is, you see, maximum likelihood, it gets different results if you initialize it from the discrete hidden Markov model, or from k-means, or from the continuous hidden Markov model, while DA has practically the same result. There's very small difference, regardless of how you initialize it. Okay, a few words about current work that we have going on. We have an ongoing project. Now this is really current work, meaning we don't really have a lot of results out. We have work going on structurally constrained speech recognition design, where we try to optimize the complexity of the structure at the same time. So we gradually trade complexity for error, a decrease on the training set, and then eventually find a point on this optimal trajectory in complexity space based on cross-validation. Another major attempt that we're just initiating maybe, is to work on the complexity reduction. That's something that would probably bother many people here about what DA is about. And there are lots of ideas of how the complexity could be reduced, because so far we haven't even bothered to try to reduce complexity. We just try to get results. So the annealing schedules, they just came out of my sleeve. I just wrote, let's do it geometrically. And of course we can probably rush between phase transitions and be careful only at phase transitions, for example. We also know where the transitions are, and we also know in what direction the split is going to be. There could be sub-sampling of the training data, so that when you're at high temperature you don't need so many of them, and low temperature you can do a sub-sample for each cluster that you're working with. You don't need to work with all the data. There is phase transition analysis that I refer to, and parallelization. Most of it is parallelizable, so you can work on different parts of the data in parallel, and you can work on different parameters in parallel, and so on. Maybe just to tell you where DA has been applied so far by other people. Most of it is just before coming for the talk, I looked up the citation index, and I was astonished to find some of the places where it's been applied. The first item is the things that are very closely related to what we did, and we have ourselves applied it in compression, communications, pattern recognition, etc. It was applied in physics, in chemistry, in astronomy, in biology, medicine, linguistics, computational linguistics. I didn't actually read many of those papers, and economics. Most recently, I did come across some papers that I read in molecular biology. People are doing DNA chips using our approach. I was very surprised. In medicine, there was a method for detecting colon cancer that was publicized last year from Princeton, something using the DA clustering method and so on. So that just gives you an idea of where it has wound up. And right in time, let's conclude. DA approach to space partitioning problems for sort of the general underlying thing that are fundamental in pattern recognition, compression, statistics, etc. Difficulties of poor local minima and piecewise constant cost function are overcome via randomization of the partition. The method was derived first in clustering and then extended by introducing structural constraint to family of optimization problems. Some sales pitch about substantial improvement over standard problem-specific and structure-specific problems. Because you see, this is a very general approach, and we got gains in all these different optimization problems with all these different structures. Many of them were problem-specific and structure-specific approaches. Some derivation and results for speech recognition that I managed to squeeze in. And that's about it. Any questions? I was actually wondering if this pile thing is what you threw at the last speaker. Yeah.
So I'm trying to see how to apply the HMM method to, well, no, okay. I'm not going to ask that question because maybe I say how to do that. But I'd like to understand the difference between assigning, between trying to get a high entropy of the assignment to different paths for a given observation sequence, and asking simply the choice at every state to be relatively equally likely among the arms. Those are different in some cases.
What we're looking at is the overall entropy, the way we're doing it. So that does allow for different entropies for different HMMs, for example, right?
Right, no, not quite the question.
Okay.
So you're trying to get a high entropy on the posterior distribution over paths, right? Now you could also try to get
on the high entropy on the classifier decision.
Well, you're classifying every observed sequence to a set of paths, to a distribution over paths.
So that's the entropy of that distribution that we are working with.
So I wanted to ask about an alternative, and whether you think this would be likely to work, which might be simpler for some other applications that I have in mind, is why I'm asking. Where instead of trying to get the entropy over the assignment to paths to be high, or to be fixed, I'm sorry, at some H0, you want to fix the entropy over the arc chosen to leave each state. So you have that's several criteria, and you either do have a multidimensional Lagrangian, or you combine them in some way.
Well, it's hard to answer this sort of on one leg here.
I'm just asking that instinct. You know?
See, the way we look at it first is that all these transition probabilities between states are just parameters of the system. We don't even view them as probabilities.
Right, but you can reconstruct, just as you can reconstruct the distribution over paths.
But the question would be, what's the objective? What's the criterion that we're looking at? If you're looking at the classification criterion, we don't care about those transitions as far as probabilities go, because they're just parameters of the framework. If you're looking at modeling problem, if you're looking at a clustering-like problem, then you may be interested in exactly these things, these probabilities, and that will be okay. And I don't know if I'm totally off the mark with respect to your question, but
yeah. Well, I don't want to hug the floor because you have to leave in about 2 minutes. Yeah. But I'm actually doing email about it.
Yeah. Ken, I thought that was a fabulous talk. I really appreciate it.
That's the kind of a question I like. You should stop here.
So I have a real simple question. So you get this output conditional density, which presumably for your choice of t is sitting. You didn't talk about rate distortion, but it's going to put you somewhere on the rate distortion curve. In those cases, you're looking at a uniform prior for that problem. What I don't see other than do next, given I know the rate distortion theorem about generating random codes, is I don't know how to take that conditional p of y given x, which is sitting on the rate distortion curve, and then generate for a particular distortion like you showed us, a single line. That was at one distortion. Then you showed us 3 spaces. It carved out 3 spaces for another distortion. How do I go from the p of y given x to the actual the quantizing line? I don't know how to do that.
No, the quantizing line is...
Well, can you answer that?
I'm trying.
Yeah, I know.
The quantization is what you get if you... Suppose you have this probabilistic solution that's that's a fuzzy kind of...
Yes, I understand.
Now, if you fixed the number of code vectors, you won't allow any more phase transitions, and you send the temperature to 0, you'll get hard lines. That's the way you would design quantizers. You climb the rate distortion curve until the point that you don't want to allow any more phase transition. You reach the size of your code book, and then you follow constraint.
So now P is going to have all of its mass, like in the 2 case, it has its mass on 2 code words, basically.
Yeah.
Then it changes at a critical temperature to 3, to 4, to
Right.
whatever.
Yeah.
And those are the regions.
Yeah. So that's the difference if you were to actually design a hard quantizer,
Yes.
or if you were to just calculate the rate distortion curve, which is really just an asymptotic result. You don't necessarily have a quantizer of this size of vector that...
And then the other question I was going to ask you, which is related, I know you didn't cover rate distortion, but you really set up a rate distortion problem, so I know it,
Yeah.
I understand it, is, so for rate distortion theory, we know that these random codes exist.
Right.
But the problem always is, okay, I have this great conditional density on how to generate these approximators Y. But now go generate a real code book. Go generate one that is close to the rate distortion, for that distortion, that rate. So you guys obviously know how to do all this practically. I mean, not just that random codes exist, but you actually generate codes.
Yeah, but again, generating codes usually are, or very often are not that close to the rate distortion curve for obvious reasons. So you can do the best you can do with a finite vector, right? Now, the rate distortion curve corresponds to when you send this length of the vector to infinity, and that's not practically
Okay, so it's not that we've gotten fundamentally around that problem. That problem is still lurking if I just...
Yeah, it may not even be possible to get... What we do want to find is what's the best code book you can find, or quantizer you can find for a given size of a code book. So that's a well-posed problem, and that's exactly the constraint problem, if you will. Okay. Oh, I'm out of here.